good evening, everyone. I'm Shweta from second year CSC. Welcome back to today's session on recursion and backtracking. So, before we start today's session, I'll just tell you what all we are going to discuss today. So, today we'll be discussing what recursion is and some problems based on recursion and why we have to implement recursion to that problem. I mean, if you see a problem, why we have to only use recursion? We can also use iterative approach, right? So, we'll see why recursion is very useful in the problems and the second thing we're going to discuss is backtracking. Backtracking is nothing but we'll be implementing recursion in backtracking, but it is a more optimized approach for a recursive problem. Okay, let's just start. What is recursion? You all know what recursion is. Can someone tell me what recursion is? Or type it in the chat box, or you can unmute yourself. What is recursion?
Function calls itself.
Exactly. A function calling itself again and again to solve a sub problem. For example, let's consider finding factorial of a number. Suppose we have to find 5 factorial. What are we doing here? We are doing 5 into 4 factorial. If we want to implement recursion for finding factorial, what are we doing? We are finding, suppose we have to find factorial of a number n, then what we are doing is we are multiplying n into factorial of n minus 1, right? We are finding we are actually trying to find answers for a smaller sub problems. Here f of n minus 1 is a smaller sub problem, right? So we are calling a function again and again to solve a sub problem, and using that, with the help of that sub problem, we are finding the solution for the problem we are actually looking for. Here, in this definition, you can see recursion is a process in which the function calls itself again and again to solve a subproblem with an extra memory buffer is called recursion. What is this extra memory buffer? We'll come to that again, but let me just tell you some three important points that we have to look for in a recursion problem. The first thing is, one second. Okay, the first thing is base case. Base case is nothing but the smaller subproblem for which you already know the answer. Like in the case of finding the factorial, what is the smallest subproblem for which we already know the answer? It is n is equals to 0 or n is equal to 1. Factorial of n is equals to 0 is 1, or otherwise the factorial of n is equals to 1 is also 1. That is the base case, which that is the smallest, the very small subproblem for which we already know the answer is called base case. The second one is recursive hypothesis. Okay, what is recursive hypothesis? As I said here, for finding the factorial of n, f of n is equal to n into f of n minus 1. Finding how a smaller subproblem can lead to a bigger one. For example, here we are using f of n minus 1 here. How can f of n minus 1 lead to the answer for f of n, f of n? That is recursive hypothesis. Okay. Then the third one is self work. Self work is after finding f of n minus 1, what should we do with that f of n minus 1 value? What actually we doing? We are multiplying n with that and returning the value as the answer for the problem we are looking for. That is, for example, if you want to find factorial of 5, f of 5 is equals to 5 into f of 4. Right. Okay. So, we are multiplying 5 with factorial of 4. So that is self work. The own effort we are going to put in the problem to find the answer is called self work. Right. Okay. Then. So now, as I said here, we'll be looking about the extra memory buffer. We'll come to that now. Now, here is a function for finding the factorial. As I said, what is the base case? If n is equals to 1, the answer is 1. So what I'm doing is, if n is equals to 0, return 0 or return 1. Then if let's say then I'm declaring another temp variable which stores the value of n into factorial of n minus 1. That is, for if n is equals to 5, I'm storing here 5 into factorial of 4. Now I'll copy paste this code here in the whiteboard. One second, guys. Is this visible? Okay.
Yes, it is visible.
Mhm. Okay, so now first of all, I'll call main function, right? Every time when you call a function, it gets pushed into a stack. Stack is a linear data structure. So if I'll push main function here because I'm calling only from the main function. I'm going to call the factorial n. Let's just consider here, for example, n is equals to 5. So first I'll be pushing main function. Then as I call f of 5, factorial of 5, f of 5 gets pushed into the stack. Okay, so f of 5, so we'll check. If 5 is not equal to 0, so we'll go on to the next line. Here temp is equals to 5 into factorial of n minus 1, which is factorial of 4. What I'm doing here is I'm calling factorial of 4. So factorial of 4 gets pushed into the stack. Again, we'll be checking. Is 4 equal to 0? No. We'll come into the next line. Okay, 4. Again, 4 is equal, temp is equals to 4 into factorial of 3. We don't know the value of factorial of 3, so we'll back again push it into the stack. The same process happens until n becomes 1, and until n becomes 0. 2, sorry, that's 2, and factorial of 1 and factorial of 0. When I'm calling for n is equals to 0, what is happening? I'm returning 1 without calculating anything. So what happens? This returns value 1. This returns value 1. So this gets popped out of the stack. For finding f, then we are in the function f of 1, factorial of 1. The temp is equals to 1 into factorial of 0. Factorial of 0, it returned 1, right? So 1 into 1 is 1. So we are returning temp. So this function returns 1. This if factorial of 1 gets popped out of the stack. Now, for if we call this function for n is equals to 2. So 2 into factorial of 1 is 1. So it returns 2. It returns 2. This gets popped out. F of 2 gets popped out of the stack. Let me clear this all. Then for f of 3, we are returning 2 for the value factorial of n minus 1, which is a factorial of 2. We are returning the value 2. Now temp is equals to 3 into factorial of 2, which is 2. It returns 6. It returns 6. F of 3 gets popped out. Sorry. F of 3 gets popped out. Similarly, f of 4, the same process happens until f of factorial of 4. Then we will be, factorial of 4 returns 24. So now this temp contains equals to 5 into factorial of 4, which returned 24. What is 5 into 24? It is 120. This 120 then again returns back to the main function. Here, let me just show you. Here we'll get the value 120. This is how the stack trace happens for a recursion call. If you understand this, we can further move on. Let's just, before that, let me just try for someone. What is the expected output? We have to get 120, right? For input 5, the value that we have to get is 120. Let's just try that before. Okay. So we got the value 120. Did you guys understand the stack trace for this problem? If you understand this, the further problems on recursion and backtracking will be easier. Did you understand this? Yeah, okay, cool. Okay, now as we understood what the factorial and all means, let's just move on to an interesting problem here. There are n friends who are planning to go to a party. They are allowed to either go alone or go in pairs. Find total number of ways in which n friends can go to the party. Let me just explain this. Consider there are 3 friends, A, B, and C. A number of they can either go alone or they can go in pairs. What are the ways that we can? A can go alone, B can go alone, and C can go alone. This becomes one. This becomes one way. Then AB can go in pair, C can go alone. The AC can go in pair, B can go alone, or BC can go in pair, A can go alone. These are the 4 ways. So for 3 friends, they are for 3 friends. What is the total number of ways they can go to the party? That is 4 number of ways. In any one, they can choose any one of the 4 ways, right? Can you try the recursive solution for this? Before finding the recursive solution, you may have the doubt why you only find the we can also try it iteratively, like using the for loops and all, right? But why should I only use recursion? That is because this is small trick, guys. If for a value for a, if you have many choices to choose, like for example, a can choose to either go alone or go in pair. You have two choices, right? Whenever they're in a problem, you are given the option to select between two choices. Then you can immediately think of a recursive solution. I'll further show this trick in other problems also. But in this problem, we suppose consider a only a. We have only friend a. He can either go alone or he can go in pair. We have two choices. Whenever you have choices, you have to think recursively. You can think recursively. Okay. Can you think of any idea or approach for this problem, or I'll just start? Any idea on how to solve this problem? Okay, I'll explain. See, there are okay, for three friends, what are the total number of ways we found? There are four ways. Let's find the answer for two friends. For two friends, they can either choose to go alone, A, B, or they can choose to go in pair, A, B. So there are only two ways. If there is only one person, A, he has only one way. He can neither go, I mean, he has to go alone for sure. So for one friend, it is one way. For two friends, it is two ways. We have found the base case for this. So in a recursion, what did I tell you? In a recursive problem, we have to take care of three parts, right? The base case. Where is that? One second. Sorry, guys. So yeah, base case, recursive hypothesis, and self work. So what is the base case in this particular problem? For n is for number of friends, the given answer is n is equals to 1 or n is equals to 2. We have to return n, which means for n is equals to 1 the answer is 1, for n is equals to 2 the answer is 2. So we will be returning 2, I mean n. The recursive hypothesis, we'll come to that now. Consider there are n friends. There are n friends a, b, c, and so on. I'll calculate answer for only A. Suppose A chooses to go alone. Then I'll be like, okay, I'll go alone. You go find number of ways in which these n minus one friends can go to the party. I've decided that I'm going alone. Then I have to find number of ways in which B, C, and so on, these n minus one friends are going to the party. So f of n is equal to, this is one part of the solution, f of n minus 1. Did you understand why? See, I'm going alone. I've decided that I'll be going alone. Then if I find the answer for these n minus 1 friends, I got the answer for when in the case where I chose to go alone, right? Did you understand this, why it is f of n minus 1, and in the case where I choose to go alone? Is it clear, this point, or should I repeat it again? Okay, fine. Then the second, what is the second choice? The A has to choose a pair. Suppose A and B chose to go alone. A and B chose to go in pair. A and B. Then there are n minus two friends. There are n minus two friends who are left to decide their choices. Who are left to decide what whether they want to go alone or whether they want to go in pairs. So I'll be like, somehow find the number of ways in which f of n minus two friends can go to the party. A and B, I'll go in pair. A and B said I'll go in pair. You somehow find the number of ways in which n minus two friends can go to the party. But A chose to go with B. What if A chooses to go with C or D or many in? So number of friends A has is n minus one. No, number of friends A has is n minus 1. It can choose any of the n minus 1 friends. So we will be multiplying n minus 1 with f of n minus 2. Did you understand why? Because see, if I choose B, number of ways I have to calculate, I have to tell others. Suppose I will allot, I'll give chance to others that you go calculate f of n minus 2. I have my answer. I'll do the self work. You go calculate f of n minus 2. Then I'll calculate the answer for n minus 2 friends. Because, but I chose, here my friend is B. What if my friend is C, or what if my friend is D? So I have n minus 1 friends here. I'll multiply f of n minus 2 with n minus 1. Then I already have one part of the solution, which is f of n minus 1. The second part is this. So if I add both of these, I'll get this is my answer. So what is the actual value of what is the recursive solution recursive hypothesis for the solution is the recursive hypothesis for the solution is f of n is equal to f of n minus 1 plus n minus 1 into f of n minus 2. Sorry for the bad handwriting, guys. Did you understand this? Why we have to multiply n minus 1 with f of n minus 2? If not, I'll explain again. Should I explain again? I'll explain. That's not a problem. Yeah, cool. Okay. Okay. Now that's all. That is a recursive solution. Now n friends problem. Here, see. If what did I tell you? The base case. For every recursive function, you have to think of 3 points: base case, recursive hypothesis, and self work. The recursive hypothesis here are n friends of n minus 1 and n friends of n minus 2. What is the self work? It is multiplying n minus 1 with friends of, I mean, the function of n minus 2 plus adding the n minus friends of n minus 1. This is the self work. The base case is if n is equals to 1, that is, if only a is there, he has only one chance. He has to go alone. So we have to return 1. If n is equals to 2, suppose a and b, they can either choose to go alone, so a separately and b separately, otherwise a, b can go together. So there are two ways. So we'll be returning n, which is 1 or 2, based on the value of n. We'll run this way. For n is equals to 3, we found the answer is, what is for n is equals to 3? What is the answer? We found it as 4. The expected output should be 4. Let's try running this. Yeah, okay, we got the answer 4. For n is equals to 2, we'll anyways be returning 2. The expected output is 2. Yeah, okay. Did you guys understand this problem? That's the solution for this. Yep, okay. Cool. I'll just clear this board. Okay, the next thing we're going to discuss is a bit complex, not a medium level difficulty problem. Wait 1 second. Okay, we've given an array n. We have an array. We have an array. The array elements are 1, 2, and 3. We have to find the subsets. What are the subsets? It is 1, 2, 3. Okay. If n is equals to 3, the number of elements in the array is 3, what is the total number of subsets that we will get? It is 2 power n. Okay. So we are, in this case, we have to get 8 subsets. In this case, we have to get 8 subsets. For this value, what are the subsets? It's 1, 2, 3, 1, 2, 1, 3, 1, 2, 3, 2, 3, and an empty subset. uh, to this, okay, now again, for every element in an array, we have two choices. Either we can choose one, or we cannot choose one. I mean, if for every element in the array, there are two options available. We either to choose it or to not choose it. What did I say? If you in a problem, if you have the choice of, if you have the power of selecting any one of the two choices, you can think the answer recursively. So, okay, now, is there any way that we can think of the answer recursively? Or you can give any ideas. If you guys have any ideas, you can please give. See, you have choices, right? In the elements, you can either choose one or no. You can either choose two or no. That's why the number of subsets is 2 power n. See, I can either choose one or no. So we have two choices. I can either choose two or no. I have two choices. Again two. Here two. So two into two into two. There are 8 subsets totally. When you have choices, you have to think recursively. Do you guys have any idea? Okay, let's just start. The array is 1, 2, 3. The question is print the total, all the subsets of the given array. Okay, now I'll consider an empty vector. An empty vector without any elements. I'll start with the first element of the array. I can I can add one to the vector, or I can just leave the vector empty. I can add one to the vector, or I can leave the vector empty. Why? Because I can either choose one, or I need not choose one. The second thing, again, I can add. We come to the second element. I can leave the vector again empty, or add two to the empty vector. Here, I can leave the vector again to be only one, containing only one, or in the vector I'll add one. Both I'll push two to the vector. By vector I mean it is just an array. Again, now I have third. I will come to the third element. Here again, I can either choose three to. I won't choose three to be pushing into the vector, or I can push three here. Again, I can, without adding three, I can just leave the vector, or I can add three here. I can push three, or I won't be pushing anything. Sorry, here I won't be pushing three. Here I'll be pushing three. Here we won't push anything. Just leave it as one. Here one, we have already have 1, 2, 3. So I won't be pushing 3 here. I'll be pushing 3. So let's just stop here. What do you observe? Here we have all the subsets of the array. In which step? Here it is n is equals to 1, n is equals to 2, and this is n is equals to 3. In the third step, we have all the subsets of the array. Here we have the base case with us. So if the number of the step we are going to find the answer for is equal to the number of elements in the array, then we can stop and then print all the values. We can print all the values. You know what? In every time you have to know this. When you have a recursive function, how it gets called is first. If I call this, it will go here. This will again go here. Again, I will get this. After this, the next function, that the next answer that I'll be getting is this 3. After that, I'll return back here. After this, we don't have any other child for this particular empty array. Then I will be going here. That is how the recursive function gets called. Did you understand how I wrote this tree? This tree kind of formation. Did you guys understand, or should I explain it again? Okay. Okay. Now we have this tree. We should just find the recursive hypothesis. What is the recursive hypothesis? We have to find the functions from which we can get the actual answer. Now, okay, we are maintaining a vector, right? So in the first, we have to call the vector two times. One, including the element. The second, in first time without including the element. The second time we will include the element in the function call. Now let's just see the code for this. subsets. Or we'll write the code now. We will not include the element. The second time we will be including the element. We will iterate through every element in the array. Let's just write the code for this now. Okay, to find out what all should be, I've taken in, I'm taking the input n here, and also taking the array elements list. So to find, we will send array. We will need. Okay. Okay. The first thing that we need is the array elements. The second is number of array elements int n, so that we will know where to stop. Next, the next thing that I need is I. This I is required because we will know we have to traverse through every element of the array, right? That is why this I is required. I'll show you why we need that. The second thing is the vector that we are maintaining here. See, here we have these vectors, right? That's why we need another vector, so that we can push the elements into the vector. We'll name it as vector. Okay. Now, what is the base case? If I equal to n, what did I tell you? If I equal to n, we can print all the vectors. We can print all now here for okay. Now for n is equals to 3. Here we have, this is a vector, right? So if we print the elements in the vector, that is the subset of the required vector. The subset of the vector we are going to pass, that is a. For this a, we will be printing the subset through this vector. So this is the vector. Okay. Okay. For j less than vector dot size, this returns the size of the vector, and j plus plus. Now we will be printing it. See out. We have this here, and we will be returning back because we know after that we no need to traverse further. Now, what did I tell you? We can either add the element to the vector or no. The first call is without adding the element. Now, this is I is equals to 0. For I is equals to 0, we will be calling this element of the array. Now it is I'll be calling the function again. I'll pass a and n. For this is I. Now this is I. I'll increment I. Why? Because I have to access the next element, I plus 1. Then I'll, without pushing anything, I'll just pass the vector. The second time what happens is I'll push back the element, which is a of I, and then call the function again, subsets. Again pass the parameters n, I, and vector. What's happening here is I will be calling this for I plus 1. Okay, now what's happening here is I'm pushing back the first element of the array, so that this gets included. In the empty vector, this is not 1. Sorry. In the empty vector, I'm pushing back 1. In the first case, we are not pushing back anything, which we are not considering the element into the vector. In the second case, we are considering the element into the vector. Okay, now let's just try running this. Okay, for input n and array elements are 1, 2, 3. The number of array elements is 3. Okay, there's some mistake. Okay, sorry. The function call in the main, we did not complete the function call in the main function. What all parameters should be passed? We have to pass a, n, and I've already declared a vector here, vector that will be passing again 0. And what is the 0? 0 is the first element that we are going to look into. That is a of 0, which is 1 in this case. That's why I'll be passing 0 instead of uh, another variable. So let's just try running this. Mm-mm. Sorry. One second. Oh, what's the mistake here? 1 minute. Can you guys find the what's the mistake here? It's a mistake. Mm, okay. Every number that we're printing is becoming 0. We are pushing a of I here. We don't push anything here. Did you guys understand the core concept behind this? I'm just trying to find the mistake. The answer we are getting 0 0 every
Can you show me the code once again?
yeah here.
So you have a vector, right? So the vector, wait, I'll try to look into it. Yeah, so, oh, sorry, I guess I was muted. The first vector is empty, right? Vec is empty,
Mm-hmm.
and I guess this is a problem. Not sure yet, but
I'm sorry.
you
Okay. Yeah. Sorry. Yeah. Please tell me. Yeah. Please tell me, reason.
yeah, okay.
Sorry.
So the thing is, the vector VEC is empty now. So I'm not
Mm-hmm.
sure whether this is the problem, but first you're passing in VEC as a parameter now, right? You're copying the vector first, so that'd be a problem. You should pass it as a reference.
No,
So
no, no. That's why. After this, I mean, without passing it as a, mm, passing it as a reference, I have. That is why after this problem, I thought of introducing backtracking, uh, with which
okay,
we'll
so
be passing a
even
vector as
it's
a
okay, it's fine. So
reference.
if that's the case, then you're passing n, right?
Mm-hmm.
So you're passing n and zero. So if I equals zero, that's going to be false in the first case, right? So
Yeah.
we'll go to OA n I plus one. No, I'm not sure what's the problem. You continue with the problem. I'll just come back with the answer.
Okay. I have a code for this. Should I just check it?
You can just check it.
1 second. I don't know what. Mm, okay. So if I is equals to n. Okay, sorry. We are outputting vector of I, which but we have to output j. Yeah, I'm sorry for that. Okay, the variable we are using here is j, but I was printing vector of I, so that's why we got the wrong answer. Yeah, we have the subsets here. 3, 1, 1, 2, 3, 1, 1, 2, 1, 3, 2, 3, and 1, 2, 3. If we want to print even the null vector, we'll just have one more if else statement here. If vector dot size if it is a null vector, this vector size is 0, right? If vector dot size is 0, then we'll just yeah, to just indicate if it is null vector, we'll output minus sign here. Okay. I think we got the answer here. So this is the null vector. Then we print 3, then 2, 2, 3, 1, 1, 3. This order is same. Look at here. Now we print the null vector. Then we print 3. Then what is the answer we got? We print 2. We print 2, then 2, 3, then 1, 1, 3, 1, 2, and 1, 2, 3. This is the same order. How are we actually traversing? We are traversing like this. This is how in every recursion we traverse. Like this. Okay? Did you guys understand this? Or should I explain again? I'll tell you a small problem here. I mean, not a problem. We'll just decrease the time complexity. What is the time complexity for this problem? It is 2 power n. Why? For every why it is 2 power n is for every element in the array. Suppose 1, 2, and 3 are the elements in the array. For every element in the array, you can either choose or you will not. You are not choosing it. So if you have two choices for everything. So if there are n elements, for n elements, you will total number of calls you are making is 2 power n. So the time complexity is 2 power n. Now, not only 2 power n, since as we are copying the vector here, this vector to this vector, I mean, in every call, we are copying the element, we are not passing the reference. If we copy the element, it takes an O of n time to copy every element in this vector to the vector we are passing into the function. So the total time complexity is n into 2 power n. So what if what if I make it as a reference I mean sending it as a copy? We'll just make it as a reference. Everything will make it as a reference. Let's see what answer we are getting. Wait, this is not the subsets we are looking for. This is something very different from the actual answer, no? Why is that happening? See, now I called for one. This is empty, first empty vector, then again empty vector, then I'll call for 1, then I call for 1, and this becomes 1, 2. The elements are 1, 2, and 3. And this is again empty vector, I'll call for 2. Empty vector, and call for 3. This is 2. This is 2 and 3. I'm including every element here. I mean the elements of the array here. This is 1, still 1. The next call is 1 and 3. Here it is 1, 2, and here it is 1, 2, and 3. What I'm doing, I'm pushing an element into the vector. If I pass it as a reference, I'm just passing the same. I'm just changing the name of the vector, but I'm not changing the values. I'm actually changing the value, the vector, the whole form of the vector in the main vector. Suppose this vector is empty. The vector I'm passing is empty. If I push back 3 here, and call this function. This vector will contain 3. With this vector will also contain 3, and the passing vector will also contain 3. That is safe here. I will show it in the diagram. If I return here, now this is empty. This should be empty vector, but what I'm having here, I'm containing 3. If I pass it as a reference, this vector contains 3, but it should be empty. When I return here, this also contains 3. When I come back here, this vector already contains 3, and then I'm pushing back 2 here. That is why we get the wrong answer. So what should I, that is where the whole concept of backtracking comes. What is backtracking? I'll just show you. Backtracking is an algorithm that tries to find the solution to a given parameter recursively. They're the same as that. Backtracking is nothing but an optimization for a recursive call, and abandons the solution that fails to satisfy the condition. I'll come to this abandoning part later, but then let's continue. In this process, the changes that we make while finding the solution is deleted or backtracked. What is the changes that we make while finding the solution? We are pushing back 3 here. Suppose example, I'm just taking an example. We are pushing back 3 here, and if I want to pass it as a reference, I have to delete the change that already made. If I push back a number, what is the opposite of pushing back? It is pop. I'll just pop the element again. If I pop the element again, pop back. If I pop back, what happens is, I'll show you here in this thing. Now after this function returns, I'm popping back 3. So again, this becomes an empty vector. If I return to back to this parent call, this is again an empty vector. There is no change that you can observe if you pop back. That is the whole idea of backtracking. That is, whenever you go into a path, you remove all the traces that you've been in the. Suppose you're going to a forest. When you're going to the forest, you will remove all the traces that you've been to the forest. That is backtracking. Okay, all the traces that already you've been, the traces that shows this person has been there is removed. That is called backtracking here. So if I pop back the element that I added, if I run this again, let's see what output that we get.
I think a popback does not take any.
Sorry, yeah. Thanks for that. Okay, now we got the same output as previous. Passing it as reference reduces the time complexity. We do not require the time to copy each and every element to the vector. So passing it as reference optimizes the solution. We need not copy each and every element into the new vector. We got the same answer. So we printed all the subset as required in the solution, as required in the question. You guys have any doubts here? Should I explain this problem again? Okay, now I have another cool question, which is rat in a maze problem. We'll look into the constraints and code ourselves. Okay, this is the problem. So you have to find a path through which the rat move from starting position 0, 0 to the final position where cheese is in n, n. List the total number of possible paths which the rat can take to reach the cheese. I'll draw a matrix here. So there's a block like this. Let's consider it as a 4 cross 4 matrix. So the rat is here and the cheese is here. The rat has to move from here to here. No, left further. A file whose first line contains the size of the square matrix. So it is square matrix, n cross n matrix. The next n lines contains the n binary values separated by space. 0 denotes an open cell, while 1 denotes the block cell. Okay, what they're trying to say is this: the whole maze is not completely open for the rat to move. There are blocks in between. Suppose let's consider the blocks to be here. These blocks are denoted by the number 1. So blocks are denoted by the number 1, and then empty spaces are denoted by the number 0. Is if there is a 0, you are free to move there. You have to find the paths with which contains only cells which are open, and finally print the total number of unique paths. Tracing the one or more cells back and forth is not considered a new path. What they're trying to say is, this is one. Sorry, wait. Let me take another color. If this is one path, you cannot go back and again come here and tell that that is a new path. We have to go through one cell only one time. The set of all cells covered in a single path should be unique from other paths. Okay, this is the input. So if the number in the matrix is 0, then you are free to move. If it is 1, you're not. That okay now. Okay, this is let us consider this as a position of the rat. And how many ways that rat can move? It can either move up, it can move right, it can move down, or it can move left. Okay, this is right, this is left, up and down. Now, if the rat is in this position, first let us consider the rat moves. Let's have this order. I mean, first let us consider the rat moves in right. If moving right side is not possible, then let's just consider the rat moves downwards. Now, if I remove this thing, okay. Now the rat moves in the right position. Again, here the rat we have a problem here. When the rat moves from this position to this position, here again we have four choices. It can move up, right, down, or left. Now we cannot move up because if I go up, I'll get out of the maze. So that is not possible. So we have one constraint with us. If we are in the corners of the maze, that is the matrix, we should not choose that path. That is corner. One constraint is the corners. The second constraint is, look at here. This is the parent cell. From this cell to you're coming to the right cell. I have a chance of going back to the same cell again. But then if I go to this cell again calls this again calls this one. This becomes an endless loop or infinite loop. I mean, there's never getting out of that loop. So what will we do there? We have another. We should not move into the uh, cell which we already visited, or the parent cell. So we have to keep track of another matrix, that is we have to keep track of another variable, that is check if the cell is visited or not. We have the second constraint. Then I have the rat chooses to come here. Then here again, the rat chooses to come here. I cannot further go right because I'll get out of the maze then. Then I'll come here. Is it possible to come here? Anyhow, any cause. Let's consider the rat came here. Is it possible to get a solution if the rat comes to this cell? No, there is no possibility. If the rat comes into the block cell, there is no possibility that the rat can reach the cheese. That is in this n minus 1 comma n minus 1 cell. The rat will never reach that. So what will the next third constraint is the blocked cell. Blocked cell. So we have a constraints with us. If we will be checking all these constraints. If any one of the constraints gets if one of the constraints is false, then we will abandon that solution. We will abandon any the here we as I said, we'll look into the abandoned word after some time. Yeah, see, we'll again read this. Backtracking is an algorithm that tries to find the solution to a given parameter recursively and abandons a solution that fails to satisfy the given condition at any point of time. So here I'll abandon the three whenever the matrix satisfies one of these three conditions. I'm abandoning the solution. I will never go check further. I will never check further to reach n minus 1 comma n minus 1 cell. We have three conditions with us. Did you guys understand these three conditions? Otherwise, I'll explain it again. So, I'll repeat that. We have to check at the corner cases. If you are down here, you cannot move left or you cannot move down. If you are here, you cannot move down. If you are here, you cannot move right or you cannot move up. Similarly, then if it is visited, see. Okay, now let me just draw another matrix. It looks clumsy here. Mm, Again, I'll consider 4 cross 4 matrix. Okay, now the block cells are this, and this. The rat is here. What are the different ways? Suppose I found this way. The next now I the next solution can be this. Sorry, the next solution is this. Okay. See here, for two different ways, this cell is okay. For the when you're finding the first solution, you're finding the solution. You're marking when whichever cell you reached, you have marked that as visited. Suppose let's use this color to mark it as something as visited. Now, if I mark something like this, it is visited. This is also visited. This is visited. This is visited. This is visited. Okay, now the second path. I have this path. See here, I've come here. See, you have already visited this. I cannot move here, but the possible solution is I can come here and find a solution like this, or find a solution. I've already marked I've already marked this path as visited. So what should I do? I should mark it as unvisited. This is backtracking again. A particular cell can be answer for multiple sub paths. This cell could contribute to the answer for multiple parts. That's why whenever you are visiting a cell, after finding the path, you have to again unvisit the cell. This is backtrack. That is, what did I tell you? The changes that we made to a particular sub problem, while returning back, we have to delete that change. That whatever change that you made, you have to delete that change. Shall we just try coding this? Did you understand all the constraints and visited and marking unvisited thing? Should I? Okay. Yeah, let's just try coding. That means problem. Okay. Now I'm taking the input n. That is the size of the matrix. And the second thing is the array. The array for taking the input, taking these inputs. That is 0 and 1. 1 means the cell is blocked. Then so what did I tell you? We have to maintain a matrix such that to know whether this particular cell is visited or not. For that, I'm again declaring a 2D matrix, uh, which starting I've declared everything to be false. That is, in any cell is not visited. Then I'm taking the input. Find paths to find before that what is the solution that we have to find here? The output should be total number of paths possible on the first line. Total number of paths in which the rat can reach the cheese is the answer. So I'll declare a global variable and initialize it to 0 count. Every time I find the path, I'll increment the count. How will I know base? So what is the base case here? Base case is when you reach the end. That is this matrix, this cell. Sorry, this cell. When will you reach this cell? If we maintain two variables r and c, that is rows and columns. If row is equal to n minus 1, this is n minus 1, and the column is also n minus 1, row is also n minus 1. If r is equal to n minus 1 and c is equal to n minus 1, I have reached the end of the matrix, and which means I got the cheese with me now. That is the base case. So what should be the base case? I'm passing the array. I'm passing the array. This array. Sorry, this. Okay. I'm passing this array and the visited array. To know everything, I should be passed as a reference. This array need not be passed as reference, but just to avoid copying the array elements, we are passing. Then we are maintaining two other variables, r and c. R and c represents the cell which we are going to check. That is, if we first we'll be starting with the 0 comma 0 cell. That's why r and c is 0 and 0 here. This n is the size of the matrix. Now the base case is if r equal to n minus 1 and c equal to n minus 1. What did I tell you? We reached the end of the matrix. That is the last cell. We'll be incrementing count. Why are we incrementing count? Because we want total number of paths. Now, there are totally four ways in which the rat can move. Right, down, here we have seen. Right, down, left and up. To move right, what value should I increment? This is column and this is row. To move right, what should I increment? I have to go here. I should increment c. So I'll be calling the function for c plus 1. Before calling the function for c plus 1, what should I check? I should check if this particular cell is safe to move or not. For that, we will have another function is safe, which tells whether the particular cell is safe or not. We will fill that is safe function later. We'll just write the main part of the code here. If to move right, we have to increment c. If is safe, I'll complete this parameters again. If is safe, only if the adjacent cell is safe, we will be moving there. Otherwise, the rat will move there. We'll again call find paths. We'll call find paths function, pass array, the same array, then visited. Okay, I forgot one important thing here. Immediately after checking the base case, what we will do is we will mark the current cell as visited, R and C is equals to true. True indicates that the cell is already visited. Okay, now we will pass the visited cell. Then to move right, what did I tell? We have to increment C. So I'm calling the function for C plus 1. Then I'll be passing in the same way. The same thing we have to follow for down also. To move down, what value should we increment? Look here. So to move down, I'm moving down. What value should I increment? We have to increment r value, r plus 1. So this r value, we have to call the function for r plus 1. Then after moving down, where are we going to move now? We will be moving to the left. To move in the left direction, see here, if we are in this position, C, I have to move left. Now what I have to decrement C this time. It is C. I have to call the function for C minus 1. To move, this is for moving left. So I have called the function for C minus 1. Then for moving, the last one is moving upwards. For moving upwards, I have to again decrement C here. Here r is equals to 0 and here r is equals to n minus 1. To move upwards, suppose consider r is here. To move upwards, I have to decrement r. So I'll call the function for r minus 1. R minus 1. Okay, we have called the functions for everything. Now we'll fill this is safe. What are the constraints that I told you? Here, I have written it here. Sorry. Okay, we have to check if it is the corner of the matrix. How do I check if it is in the corner of the matrix? Okay, it is the let me just write the coordinates here. It is 0 comma 0. It is this corner thing is n minus 1 comma n minus 1. If the suppose wait, if this function if c plus 1 is greater than n, see here, this is n minus 1. This row sorry, This row is n minus 1, right? If I call for n, if suppose n minus 1 is incremented to n, then it will go out of the matrix. So what the first thing is, if the I represents here, I represents rows, j represents a particular column. Okay, so if I is greater than n, or if j is greater than n, that is, if we go out of this out of here, I mean, let me just show it here. If we go, if we go here, or if we go here, that is, if I is greater than n or j is greater than n, it is not safe. We have to return false, or j is greater than n, or
uh, the indexing goes from 0, right?
yes, yes,
So
is greater than or
uh,
equal to n.
yeah.
Sorry, yeah, thanks. Or now, or if I is less than 0, there's a chance that you are in this position, and you're calling the function for left. You're decrementing the column value. Then if the column here is already 0, and if you decrement it, it becomes minus 1, which does not exist. Again, we are going out of the matrix. We are going out of the matrix. So if I is less than 0 or j is less than 0, we return false, which means that particular cell is not safe. If here, if it is returned false, this function is not at all called. Then the second, what is the second constraint that we thought of? Visited. Now we've visited or blocked. If a particular cell is visited or the particular cell is blocked, we cannot go there. We abandon that whole solution, where from which, wait, if any in any way the rat reaches this block, we won't get any solution because the rat cannot enter the block at all. So we abandon this cell. Again, if visited, we are having, we are maintaining another vector visited, right? If visited of I j is equal to true, or if the cell is blocked, how it is mentioned, the array of that particular cell is 1. If it is 1, then the cell is blocked. So AR of I and AR of j is equal to 1. In both of these cases, we cannot go to that cell. So sorry, we will return false. In any other case, we return true, which means the particular cell is good to go. We can go to that cell. Now we have fulfilled all the constraints here. See here, we are not we checked for the corner cases. We checked if the cell is visited. We checked if the cell is blocked. Hmm. Now there is another important thing that we have to know. As I said that one particular cell, this particular cell, this particular cell can be can be answer for multiple parts. So let's just take this particular cell here. This cell can be answer for this path, or that cell can be answer for this path. So what should we have? We marked visited here. For that cell, we marked visited here. After finding solution for that path, we will mark it as unvisited. We have to mark it false, so that in the next call we can use that cell to find another solution, another path. So we will make it false. We made calls for four different directions. We checked if the cell that we are going to is safe or not. Then we are marking, we will mark if the cell is visited. Then at last, after completing all the function calls, we'll mark it as unvisited. Now let's fill this thing. It is ARR visited. And okay, now this function call is for moving right, which means I should pass r comma c plus 1 comma n. The same parameters that we use for the function call of find paths will be used for is safe also. So I can just copy paste this. This is for moving down. Moving down, that's why we use r plus 1. And this is for moving the left side. Moving the left side. And this is for moving up. Okay. Now let's just check the number of ways that we get. I'm outputting count, the value of count here. As we are after reaching the last cell, that is n minus 1 comma n minus 1, I'm incrementing count. Total number of ways that we have for this in this case is 4. Let's just check the answer in the, yeah, output is 4. We got the output. We'll try submitting this code in the website. Yeah, 1 minute, guys. Okay, now that's the correct answer. Uh, to just summarize, what we did is we want to check if the cell we are going to is safe or not. For that, we created one function called is safe. Created one function called is safe. In this essay, we check if the cell we are going to is inside the matrix. That is, it doesn't cross the matrix. And the second thing that we check is if the cell is visited or if the cell is blocked. If any of this is satisfied, then we return false. That is, we cannot go into the cell. This is called abandoning. In backtracking is nothing but optimization of the recursive solution by abandoning some sub problems which will never lead us to the actual answer. So if any of this is true, we will be returning false. Otherwise, we will return true. And in the find, in this if say then in the find, we will call the function again for every cell. Here, see. Let me just draw. Looks clumsy here. Okay. So it is nothing but I will find I have the answer for this particular cell. You go find the answer if I start from this cell. Okay, that is recursion. I'll do my self work by finding the answer. If you go find the answer for all the paths starting from this cell, I will do my self work and find the total number of paths starting from 0 comma 0 cell. That is why I'm calling the function again for the left down, sorry, right down, left and up calls. Anyhow, if you find the answer for the adjacent cell, I'll do my self work and increment the count. As we are calling the function from the starting cell 0 comma 0, and we when we reach n minus 1 comma n minus 1, we will be incrementing the count. That's all. And we have to make sure that whichever change, whatever change that we do to a particular sub problem, we have to delete that change. That is, when we mark something as visited, after finding the path, we have to mark it as unvisited. That is, we have to make it false so that that cell can be used for another sub problem, another path. Okay, this is the core concept behind backtracking. This is just an introductory class. I have in the resource sheet that we will be providing you. We have some good problems. You can try that, and if you have any doubts, we could discuss it in our Discord server. So, do you guys have any doubts to this point? Did you understand this problem? Yeah, it is interesting. We have many. There is a problem called n queens problem. It is bit difficult, but If we there are a lot of tutorials on YouTube. We can just check that and learn. Thanks, Jason. Yeah, if you guys have any doubts, you can please ask it now.
I think you have a doubt. Do you have a doubt?
Shashwini, do you have a doubt? No.
It's
Okay.
clear.
Okay. Fine. Cool.
So is the session over, Sweta?
Yeah. Yeah. That's it. If
Yeah.
there
Okay.
are no
So
doubts, we can.
as we were talking about in the beginning of the session before we started, I think this will be the last session for the online series now. We still have two more sessions for dynamic programming in graphs, right? So these two sessions will be long. Like we had math session for 2 days, right? So it will be similar. Like dynamic programming may extend to 2 or 3 days, and then graphs may extend to 2 or 3 days. And we are not sure how I'll do that because the college is going to reopen now. So we'll meet. Can you stop the recording?
Yeah. One sec.
Thank you.